So now we will define the two important specifications of the first order system. It is for all, even for second order system, the same definition will be used, but there the final expression will be different. So here first we need to define the rise time and the settling time. When it comes to second order system, we have something called as maximum peak overshoot. We have delay time. So that will be dealt in the second order system. So coming to the rise time, it is time taken for the response time taken for the response from 10% to sorry, I'll, time required for the response to rise from 10% to 90% of its final value. This is the definition of rise time. When it comes to second order system, there is a slight difference in the definition. Okay, so coming to settling time, so we have already defined the settling time. It is the time required to reach and stay. This is important, to reach and stay. Some many responses will reach within the 2% tolerance, but it will not stay within that 2% tolerance. So this becomes very important, to reach and stay there within the 2% tolerance. This is very important, to reach and stay within the specified range, within the specified range of final value, of its final value. Now this range can be 2% or 5%. Now in this we will consider the 2% range. We will stick on to the 2%. So this is the definition of settling time. Other than this, we have delay time, we have peak time, we have maximum overshoot. Now these are not visible, or these are not very you cannot define these terms in first order system, but when it comes to second order system, these are very important. Now other than this time specification, we have something else which does not fall into the time specification, but it is also a very important parameter when it comes to analysis. So that is steady state error. Steady state error, that is E of SS. So this is nothing but, it is, now we know that the error signal, I'll first write the definition of it. It is the difference between actual output, actual output and the desired output as time tends to infinity. As time tends to infinity. So this is important. It is the difference between actual output and the desired output at time t tends to infinity. This becomes very important. Okay, so with that, we will define it as ESS is equal to limit t tends to infinity E of t, where E of t is the error signal. We have seen what is error signal in our previous classes. So this is limit t tends to infinity. E of t is nothing but the difference between actual output and desired output. So, uh, yeah. So actual, I'll just write, yeah, actual output will be, not actual, the desired output will be R of t, and the actual output is C of t. Now, why I have just interchanged, because always sometimes we take R of t first and then we take C of t. So error is nothing but R of t minus C of t. Even in the block diagram, we have seen that if this is the block diagram summation block, so R of t is positive and you give negative feedback, that is C of t into H of t. H of t is the response. So this is negative. So this is the definition of steady state error. Now this is in time domain. Time domain. Now the same thing can be written in frequency domain. So in that, the frequency domain, the steady state error will be equal to limit s tends to 0 s into E of s, or limit s tends to 0 s into R of s minus C of s. Now, how did we come up with this frequency domain? This is with the help of final value theorem. This has been dealt in your Laplace transform in your engineering mathematics. Final value theorem. So, this will give us the steady state error in frequency domain, and the above equation will give us the steady state error in the time domain. So, there are two way of calculating the steady state error. Okay, so normally we have all the C of S value in S domain, and we know R of S in S domain. So when in order to avoid the simplification or the conversion of frequency to first time domain, we can directly find out the steady state error from the S domain itself, because most of the time the transfer function will be in S domain only. If you have to find out steady state error, you need to convert it into time domain and get the steady state error. So that can be avoided if we go for this second equation. So this is the definition of different time domain specification. So now one by one we will just derive it within a small time. So first one is the rise time. So rise time. So it is time taken for the system to reach 10% to rise from 10% to 90%. 10% to 90%. So here your C of t at 10%, the time will be the time taken, I'll take it as t1. And for C of t to reach 90%, the time taken, I'll take it as t2. So this will give my rise time tr is equal to t2 minus t1. So for that, first I need to calculate t1. So at t is equal to t1, the response is 10% of its final value, which means that C of t is 0.1. This is equal to 1 minus e to the power minus tr by capital T. So when I simplify this, I'll get the value of tr is equal to some value. Similarly, at time t is equal to t2, C of t will be equal to 0.9, because it has reached rise to 90%. So it is equal to 0.9. This has to be This is t1. 1 minus e to the power minus t2 by. So this will give us certain value t1, and from when we simplify this equation we get t2. So the difference between t1 minus t2 will be equal to rise time. So get the difference of these two. It's a small homework for you, work for you all. It has been already discussed in the class, so I'll not get into detail. Okay, so that will give us the rise time. So when you do the simplification, you will get it around 4.4 divided into t, or 4.4 divided by 1 by t. That is the definition of rise time. Similarly, for settling time, for settling time, so it has to be within the 2% value. So your C of t should be equal to, within the 2% is normally 0.98 times of the final value, or 98% of the final value. So that will give us the settling time. So when I substitute e to the power minus ts by capital T is equal to 0.98. So then the ts value is obtained around 3.9 into t, or we also write it as 3.9 divided by a, where a is equal to 1 by. So this is approximately, so this is approximately equal to 4 times 4 into a, or 4 times the time constant. This will get around 4 times the time constant. So this is rise time and this is the settling time. Okay. So the next one we have the steady state error. We have steady state error. That is nothing but ESS is equal to limit t tends to infinity r of t minus c of, this is equal to limit t tends to infinity, r of t value is 1 minus c of t is 1 minus 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 becomes plus e to the power minus t by capital T. So when you make this, you will get, so this and this gets cancelled, and as t tends to infinity, that is minus infinity value is almost equal to 0, because it is 1 by e to the power infinity. So e to the power infinity will be equal to infinity. So 1 by infinity will be equal to 0. So I'll write it again here so that it is easier for to understand. This is e to the power minus infinity is 1 divided by e to the power infinity. So this is nothing but 1 by infinity, and it is 1 by infinity is always equal to 0. So we see that the steady state error, the steady state error for a first order system, for a first order system with unit step input, with unit step input is 0. So what does this mean? It means that once you have attained the steady state value, so once you have attained this step, once you have crossed the settling time, the final value and the steady state value will be 1. So this is the desired, this is the very favorable characteristics of an equation. Okay, so at some point t equal to infinity, or when the system reaches the steady state, your actual input and your desired input both are same. So This is what steady state error equal to zero signifies. So this is one of the important characteristics of first order system with unit step input. Now here this is dependent on the input. Okay, so the input plays a very important role. If you go for some other input like ramp function or impulse function, this value may not be same. The steady state error, the settling time, as well as the rising time, they may not be same. And the steady state error will differ actually. So we will see how it changes in the next video. Thank you.